sure we're all familiar with vectors in 3 dimensions, but I'll just give some examples. So the vector 1, 4, 3 means we go 1 in the x direction, we go 4 in y, and I've walked the wrong way really if we're going to do a 3-dimensional plane. We go 4 in the y direction, and then we go up 3 in the z, and that will give us some point in 3-dimensional space, okay, uniquely. And just to note, we can write this as I plus 4j plus 3k, where I is equal to 1, 0, j is equal to 0, 4, 0, and not 0, 4, I see 4j is equal to that, but j is equal to that, and k is equal to 0, 1. And you can see if you do this, you will get this vector. That's just these ijk are essentially just the unit vectors like such, and then using those you can get across the whole plane. But anyway, we might go more into that on another day. We're going to look at the vector equation of a line, and this takes the form r is equal to a plus mu d. R, a, and d are vectors. R is the general point of a vector on the line. So this equation describes a whole line in unit space, not a point. Mu is some like scale factor. Not vector, scalar, obviously. It's called scale factor. What it allows us to do is change the length of our direction vector here, which is the vector analog to the gradient. So you might think, so this mu here can change, not mu, lambda can change values. And the best way to do this is to draw a graph. Let's just scroll down a little bit. That's x, that's y, and that's z. And if we have some straight line here, then the way we describe this line is we find any vector, so any vector at all, that gets us from the origin onto the line. A is just some point on the line, any point, okay? And then we describe a direction vector that runs parallel with the line. And that means that if we do a plus b, or a plus any multiple of b, we stay on the line, we move up and down the line. And then choosing, like ranging lambda from minus infinity through to infinity, we cover every single point on the line. So what this equation tells us is with a and b, you can get any point r on the line using this scale here. It's similar to y equals mx plus c in the sense that m is the gradient, our direction as such, and c is our intercept, which is essentially a fixed point on the line that we have to pass through, and then that fixes the line. It has to go through a point and it has a certain gradient. But in 3 dimensions it becomes a little bit more complicated, and then x is like our scale factor as such, and r is like our y. Okay, when arranging through values of x, we get all the values of r, of y, but by arranging through lambda, we get all the r. Note that this is not unique. Like I said, we can pick any a such that it gets us on the line, and we can also pick any direction vector. So if we have a direction vector, any scalar multiple of that is a direction vector, so we can choose that too. We can also have the pointing the other way. B could be pointing up this way on the line. Okay, it doesn't matter. So if you ask 10 different people how to come up with a direction vector equation of a line, you get 10 different answers. In the upcoming videos, we're going to look at the Cartesian form for lines in 3 dimensions, and also do some calculations about when lines intersect, parallel, and etc. If you do have any questions, let me know down in the comments. If you enjoyed this video, please be sure to like, subscribe, and I hope to see you in the next one.